We have learned that energy inside a system can change in two main ways, through heat and through work. When heat, delta Q, is added to a system by its surroundings, work, delta W, is done by the system on its surroundings. The internal energy, delta U, of the system changes. In simple terms, this means that the energy supplied to the system is partly used to increase its internal energy and partly to do work on its surroundings. This idea is summarized in the formula called the first law of thermodynamics. Delta Q is equal to delta U plus delta W. Let's go through another perspective of the same equation. This law, that is delta Q is equal to delta U plus delta W, tells us that the heat added to a system equals to change in the internal energy plus work done by the system on its surrounding. Now let's look at it another way. Delta Q minus delta W is equal to delta U. This equation tells us that the change in the internal energy delta U depends only on the initial and the final states of the system, not on how it got there. Imagine a gas transition from one state to another represented by point P1 having the coordinates of P1, V1 to a point 2 having the coordinates P2, V2. Various routes such as path 1 and path 2 are conceivable for this transition. However, irrespective of the chosen path, the alteration in internal energy remains constant. Although the quantity of heat added and the work accomplished may fluctuate based on the chosen path, the disparity between the heat and work, delta Q minus delta W, remains constant. This is known as path independence. As illustrated in the graph, the area enclosed by the PV diagram represents the work done. For instance, path 1's work is delineated by the red slanted line, while the yellow lines illustrate the work done by path 2. It is evident that both the heat and work are path dependent, while the internal energy delta U remains unaffected by the chosen path. For instance, in a scenario where there is no alteration in internal energy, that is, delta U is equal to 0, all the heat supplied to the system is utilized by the system to perform work on its surroundings. Therefore, delta Q is equal to delta W. This further emphasizes the concept of path independence and its implications. Energy within a system can be either added or removed, resulting in positive or negative values respectively. Positive values indicate energy added to the system, while negative values signify energy removed from the system. Understanding this positive and negative energy value is crucial in analyzing energy transfers within a system. Now, let's explore a specific example of phase transition in water from liquid to vapor. In the animation, we witness an aeolipile, a device driven by a steam, representing the transition from liquid to vapor phase. As heat, delta Q is absorbed by the water molecules gain energy. This energy is then utilized to perform work, delta W, as seen through the motion of the sphere. Through this visual representation, we can observe how heat absorption leads to work done, illustrating the principles of the first law of thermodynamics. Let's consider a specific example with water transition from liquid to vapor. When 1 gram of water changes its phase, it absorbs heat delta Q and work done delta W. The change in the internal energy delta U can be calculated using the equation delta Q is equal to delta U plus P into delta V, where P is the pressure, delta V is the change in the volume. In this case, most of the heat added goes to increase the internal energy of water during the phase transition. We have learned that the first law of thermodynamics is all about the energy conservation within a system. It tells us that the total energy of a system remains constant over time. This means that energy cannot be created or destroyed. It can only change forms. Let's consider the different cases. Constant volume, called as isochoric process. When volume V is constant, delta W is equal to 0 because there is no work done against volume change. So the equation simplifies to delta Q is equal to delta U. Constant pressure process, called as isobaric process. In this case, delta W is equal to P into delta V, where P is constant pressure and delta V is the change in the volume. So the equation becomes delta Q is equal to delta U plus P into delta V. Constant internal energy process, called as isothermal process. When internal energy delta U is constant, that is, delta U is equal to 0, which means all the heat added to the system, delta Q, goes into doing work, delta W. So, delta Q is equal to delta W. Adiabatic process. In adiabatic process, no heat is exchanged with the surrounding, that is, delta Q is equal to 0. So, the equation simplifies delta U is equal to delta W. Now let's go through the reversible and irreversible process. The equation holds for both reversible and irreversible process. However, in the reversible process, delta W and delta Q can be calculated differently. Reversible process are changes or the process where thermal equilibrium is maintained with the surroundings throughout. When the process is reversed, the system returns to the same equilibrium conditions. Irreversible process are changes or the process where the thermal equilibrium with the surrounding is not maintained, or it is difficult or impossible to return to the original conditions once the process is completed. Now let's go through the practical example of the reversible process. Both melting and freezing occurs at constant temperature under equilibrium conditions. This means that if you reverse the direction of the process, you can return to the initial state. The reversible nature of this process is evident as you can alternate between the two states, that is, ice to water and water to ice, simply by changing the temperature of the surroundings. Let's go through the example of irreversible process. Imagine original hot and cold water separately. Once the water is mixed, the process cannot be undone to return to the original state. Reversible work, delta W reversible. In the reversible process, work done is calculated using the equation delta W reversible equal to minus integration of P into dV, where P is the pressure and dV is the change in the volume. This integration represents the reversible work done by the system against the infinitesimally small change in pressure. Reversible work maximizes the work output for a given change in energy. Reversible heat transfer. Delta Q reversible. Heat transfer is reversible process can be calculated using the relationship between the entropy changes delta S and the heat transfer delta Q expressed as delta Q reversible is equal to T into delta S, where T is the temperature. In the reversible process, entropy change is reversible and directly related to the heat. Now let's go through the application of first law, energy transformations. The first law of thermodynamics helps us to understand how energy is transferred and transformed within a system, whether it is a change from one form to another or being transferred between different parts of the system. The total energy remains same. Efficiency. Understanding the first law helps engineers design more efficient systems by carefully considering how energy is transferred and utilized within the system. They can minimize waste and maximize useful work output. Heat engine. The first law is fundamental in the study of heat engines, which are devices that converts heat energy into mechanical work. Engines like car engines and steam turbines operate based on the principles outlined in the first law. Thermal comfort. The first law also has implications for our daily lives. It helps us understand concepts like insulation and heating, cooling system in buildings. By managing heat transfer effectively, we can maintain comfortable temperatures indoors while minimizing energy consumption. Environmental impact. The first law reminds us of the importance of energy conservation for environmental sustainability. By using energy more efficiently and exploring alternative energy sources, we can reduce our environmental footprints and mitigate climate change. Overall, the first law of thermodynamics is a powerful principle that governs energy flow and transformation in all types of systems, from microscopic scale of atoms and molecules to the vastness of universe. Now let us solve some numerical. This numerical is based on constant pressure. Suppose we have a gas confined in a rigid container with a volume of 1 meter cube. During a constant volume process, the internal energy of gas changes by 500 joules. Calculate the heat transfer and work done during this process. Given delta U is equal to 500 joules and delta Q is equal to delta U plus delta W. Since volume is constant, delta W is equal to 0. Therefore, on substituting the values of delta Q, delta U, we get work done as 0. Now we will solve the next question related with constant pressure process. Consider a gas undergoing a constant pressure process where it expands from an initial volume of 2 meter cube to a final volume of 4 meter cube. If 1000 joules of heat is added to the gas, calculate the work done by the gas during the process. The pressure of the gas is 1 into 10 raised to 5 Pascal. We know that delta W is equal to delta V, and delta V is volume final minus volume initial. Therefore, we get delta V is equal to 4 minus 2 is equal to 2 meter cube. Therefore, delta W on substituting the values of P and delta V, we get 10 raised to 5 into 2 equals to 2 into 10 raised to 5 joules. Now let's solve a question related with isothermal process. A piston contains 0.5 moles of an ideal gas at a constant temperature of 300 Kelvin. During an isothermal expansion, the volume of the gas increases from 1 liter to 2 liter. Calculate the heat transfer and work done by the gas during this process. Given T is equal to 300 kelvins, V initial, that is 1 liter, V final is equal to 2 liter. Since the process is isothermal, therefore delta U is equal to 0. Our equation delta Q is equal to delta U plus delta W reduces to delta Q is equal to delta W. Now, using the ideal gas law equation, PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, and R is the gas constant, and T is a temperature. Since temperature is a constant, pressure must also be constant. Therefore, delta W is equal to minus of delta Q is equal to minus nRT ln of Vf upon Vi. On substituting the value and simplifying it further, delta W is approximately equal to minus 2491.75 joules. Therefore, delta Q is equal to plus 2491.75 joules. Now let's solve a question based on graph. Figure below shows two paths that may be taken up by a gas to go from state A to state C. In the process A to B, 400 joules of heat is added to the system, and in the process B to C, 100 joules of heat is added to the system. Then we have to calculate the heat absorbed by the system in the process A to C. Now, for the process A to B is isochoric, that is, change in the volume is equal to 0. Therefore, work done is equal to 0. Then, from the first law of thermodynamics, delta U is equal to delta Q is equal to 400 joules. Process from B to C is isobaric, that is, pressure is constant, given as 6 into 10 raised to 4 Pascal. From the first law of thermodynamics, delta Q is equal to delta U plus delta W, which is equal to delta U plus P into delta V. Substituting the values of delta Q as 100, pressure as 6 into 10 raised to 4, and change in the volume as 4 into 10 raised to minus 3 minus 2 into 10 raised to minus 3, we get 100 is equal to delta U plus 120. Therefore, delta U is equal to minus 20 joules. Now, total change in internal energy from A to B and B to C is 400 minus 20 is equal to 380 joules. Now, for path A to C, work done is equal to area under the curve AC, which forms a trapezium. Work done W is equal to half of sum of parallel sides into distance between these parallel sides. Therefore, delta W is equal to half into bracket 2 into 10 raised to 4 plus 6 into 10 raised to 4 bracket close into bracket 4 into 10 raised to minus 3 minus 2 into 10 raised to minus 3 bracket closed bracket close. On simplifying it, we get delta W is equal to 80 joules. Substituting the values of delta W 80 and delta U as 320 in substituting in equation for first law of thermodynamics, we get delta Q is equal to 400 joules. As we come to the end of our discussion, I would like to encourage you to like, share and subscribe for more insightful content. I am Avinash from www.jnet.com signing off. See you in the next video, and until then, happy learning.